I'm not sure I'll get through this in 30 minutes, so I can start now. But I'll do a brief intro. My name is Phil Bedard. I'm from Cisco, obviously. I work as a TME in Cisco, mostly focused on network architecture. I've been at Cisco for about 2.5 years, but I spent around, I'll say, 20 years working for service providers. So after 2 years, I still have some brain cells left, but next year they'll probably be gone. So the talk today is really, the intersection of optical transport and routing in next generation networks. I use the word intersection because people have talked a lot in the past about convergence between IP and optical transport. It really hasn't paid off that much in the past, but really this is kind of a new way of looking at how we converge those two networks in the future, kind of enabled by innovation that's coming, both on the optics side, as well as some things on the router side that's being done to really enable a next generation architecture that's truly converged. Kind of the quick agenda. I will kind of take a brief look at what current multi-layer network architectures look like, and that really, when I say multi-layer, I mean an IP routed layer, and then an underlying optical transport layer, and what that looks like, what that design looks like, what are some of the current issues with those types of deployments. And then we'll take a brief look at the next generation architecture, what the components are of that, what really are kind of the building blocks that are enabling this in the future. And then, time permitting, we'll look at a modeling example of a real network to see how this new design stacks up to what we would say is a existing or current multi-layer design. But I'll take a step back, in the beginning and kind of talk a bit about, how topologies have evolved for IP networks over the years. The first IP networks when they were deployed, really just hop-by-hop IP networks. And when I say hop-by-hop, it really means at a packet layer. And that would have maybe originally been deployed years ago using an ATM network, and we connected routers via ATM networks, but an ATM network is still a packet network. And over time, things evolved to have a network where we needed to, potentially move away from having traffic pass through every router in a ring. The main thing that drove that was traffic demand and cost. Router interfaces have been pretty expensive for a long time. So we found new ways or novel ways to bypass router interfaces based on A to Z traffic demands. Really, the traffic demand, drives what the topology of the network looks like, or at least the logical topology. So that really drove the need to have like an underlying system, that can make better use of things like the fiber optic, transport between locations. Because like I said, the routers didn't really keep up with capacity, and they're also very expensive to deploy in that sort of hop-by-hop ring manner. And it really kind of led to multi-layer networks where I do have a separate optical transport layer, and then I have an IP routed layer or packet layer on top of that. And those are typically deployed today in two different ways. The one on the left there I call the router plus muxponder model. You could call that IP plus DWDM. But that really kind of fits the way many networks are deployed today with a routed layer and then a completely separate photonic layer underneath that, where I'm using active elements in that network. So that's with muxponders, it's with active ROADMs doing add drop. And there may be other components in there, such as amplifiers that are used for longer distances. Another method of deploying this is what we call IP over WDM. The difference between these two is with that router plus muxponder model, the wavelength on that network is being launched by the optical transport system. And the IP over WDM model, it's being done on the router itself. And we still see a lot of deployments of that, mainly in lower speed networks, access networks, aggregation, utilizing things like CWDM and DWDM with 10 gig optics. And now we're seeing more of it 100 gig, 200 gig, kind of CFP DCO, but still mainly in, I'll say, lower speed aggregation networks and not really high bandwidth metro, regional, and long haul backbone networks. We also see a lot of this in DCI where there's shorter reaches involved, between those different router elements. So we've seen things like 100 gig, PAM4 optics become, popular for DCI. recently, but not really used in metro, regional, or long-haul networks. Here's a bit of kind of a linear view of what these different connectivity types look like. And I'm not going to read through all the bullet points, but it's really, you have connections over dark fiber, and obviously that's just connecting two routers back to back over standard optics, or they may be long reach optics of some sort if you have a longer distance involved. But it doesn't make the best utilization over a piece of fiber, or it doesn't make the best resource utilization of fiber, which is a fairly expensive resource. You're really limited to just the speed you have in those two optics that interconnect those routers. The second type is the one that I just spent a bit of time talking about, and the way that most, I'll say, higher bandwidth networks are deployed today when you look at regional and long-haul networks to really maximize what you get out of a piece of fiber. And that does have multiple active elements where I do have a transponder, I have a ROADM that's grooming that traffic onto the fiber. And you can see kind of in the transceiver view there, the number of optics I need to complete that connection end to end. I have typically a gray optic connection, or back-to-back gray optic connection between a router and a transponder or a muxponder. And typically, you either have some sort of, these days it might be a CFP2 DCO or ACO optic out of a transponder shelf, or it may be an integrated, kind of photonic interface that's actually putting that wavelength out to go onto the piece of fiber. But there's a lot of components that are involved in that type of network. It uses more power. And obviously, from a space power efficiency perspective, it's a lot more than we're doing over dark fiber, but you do unlock the full capacity of that piece of fiber. IP over WDM, again, there's no transponders involved in this. The wavelengths are launched off of the router itself. And in this use case, I just have kind of a simple mux that's connecting those two elements. It still allows me to get better utilization out of the fiber between those two endpoints, but without all the active elements that are involved. But in this case, I can't bypass one router through a ROADM. Every hop is point to point between the two routers. So what are some of the issues with these current kind of IP plus optical and IP plus DWDM deployments? And these aren't new bullet points. If you've looked at anything around packet optical convergence in the last 10 or so years, these kind of always come up. The big one is that I'm operating multiple kind of opaque networks. If I'm using back-to-back gray optics between a transponder and a router, there's really no information sharing. They're completely different control planes between those two networks. Typically on the transport side, the control planes are wholly proprietary. We had this notion of using GMPLS, and GMPLS has been worked on for many, many years. It never really kind of satisfied its original goals of creating this kind of multi-layer control plane that we could use between those two layers. So today there isn't much work done between the router layer and the transport layer in trying to make those elements talk to each other. Something that's probably a bit newer is this notion of different protection schemes. Optical restoration, which is restoring a circuit on the optical network, so it does not go down on the routed network. It's become a little bit more popular, but when you restore paths on an alternative, fiber path, the routed network really has no idea, what that path is. If you're doing, constraint-based routing where you're dependent on, shared risk link groups or path disjointness for services, it's very hard to share information between those two different layers. So you end up with mismatch protection, and potentially, in certain failure cases, your service is going to go down when you don't expect it. And then just organizational silos and time or speed to actually turn up services or turn up circuits. In many organizations, there's a separate IP group from a transport group. There's a few where those are combined groups, but very often they're different operations teams, they're different engineering teams, they're different architecture teams. So it takes a lot of work in order to plan those networks, to engineer them, and then ultimately operate them. And you're typically duplicating some of the same tasks over and over when it comes to those planning functions. So this is kind of the fancy 3D model of what a lot of these, I'll say, higher bandwidth IP networks look like today, and it's really two layers. You do have that routed layer that's connected via gray optics to this ROADM layer, and the ROADM layer really is what gives you any-to-any connectivity between the routers on that network. I make the point of this network does not have OTN services on it. If you're using OTN, just add another layer to the network that's sandwiched in between the routed layer and the underlying optical transport layer. So that's, so if you had that OTN layer, it just adds more complexity to the network. At least that's my worldview on OTN. But so how does this evolve? Like, how does this change, and how do we how would we look at building networks in the future? Sort of the second one, and this is kind of where we're focused in the future on how we build really kind of high bandwidth networks in the future. And you see that this is no longer has that ROADM layer underneath. It is just a bunch of interconnected routers with those wavelengths being launched off of the routers. People don't like me to call this IP over DWDM at Cisco, but really that's what it is. So it's a reimagining of that. But with innovations, it doesn't have the drawbacks of the previous iterations of this, and I'll explain a bit more of that in the following slides. But when most people look at this, it looks like a lot of Cisco routers, and we're just trying to sell you more router ports, which is true. But we're also an optical transport vendor, so we're talking about eliminating those layers for good reasons. Let's put it that way. Oh, I think some of my icons left the slide here. But so when we look at that, and I'll go back, so I really call this a single layer hop-by-hop fabric. So you'll see people at Cisco use the term hop-by-hop. This is kind of really what we mean is this single packet layer, unified packet layer without the ROADM network. And this is really talking about like what's left of that optical transport network when I move to this type of architecture. You still have C-band and L-band multiplexers. We want to make the most efficient use of the fiber that we have. So we still need multiplexers to put those signals on the fiber. You're still going to have amplifiers. You may have local amplifiers where you need them. You have ILAs. If your distances are greater than say 80 kilometers, you still need amplifiers in this solution. That's not magic. We haven't solved those issues. So you still have some portions of the photonic network. What you don't have is you don't have muxponders, you don't have transponders. That function has been built into the router optic. What you also don't have is a ROADM network. So there's no any-to-any multi-degree ROADM network that you're using anymore. The switching all goes through the IP and packet devices. You also don't have to worry about regen. And some people may say, well, a router is a really fancy regen, and that's absolutely true. But you no longer have to worry about that at the photonic layer of the network. Since I am hop-by-hop between routers, I no longer have to worry about that. As I said, the last kind of 4 bullet points should be things that aren't in the network anymore. And I get this question. So I mentioned convergence, and convergence being something that people have talked about many times over the past 10 to 15 years, and how that we can either merge these networks, either at layer 3 through things like IP over DWDM. Cisco did this with the CRS many years ago, and there were large networks that were built using these 40 gig line cards. The reason this really didn't, I'll say continue to be mainstream in a lot of networks is really kind of the bottom bullet point is density. There's always a density penalty with using these types of interfaces in routers. And that's always been the case. And that's really the main problem in the future that we're innovating to solve, is to not really have a density penalty when you look at these types of optics in routers. The other thing is cost. Router cost is pretty expensive. IP interfaces in the past were pretty expensive. So bypassing those routers on the photonic layer was a more inexpensive proposition. It followed the traffic demands that I needed. So like I said, everything generally comes down to density and cost. And I mentioned a little bit earlier around router capacity. With a lot of the really high bandwidth networks we have today, I couldn't simply build a hop-by-hop ring-based network because routers didn't have the capacity end-to-end to fulfill those bandwidth needs. And I think with the advancements in the future, things like 400 gig that I'll talk about, we finally kind of unlock the capacity we need to make this more applicable on a wide scale outside of specific kind of niche applications. So what are some of the short benefits that you get out of going to that, single layer hop by hop architecture? Protection is all done at the IP layer. That's kind of an easy given one. In many networks today, they do all of their protection and restoration at the IP layer anyways. I would say the majority of networks do, but if you are using something like optical protection and restoration, this simplifies that quite a bit. IP network utilization, and that's really the kind of the StatMux equation. If I'm using bypass with high capacity circuits like 100 gig and 400 gig, I'm really building a lot of capacity that I'm not potentially utilizing. If I build things in more a hop by hop manner, then I can get the gains of StatMuxing at every hop across that network. Wavelength efficiency, and I've got a next slide about that I'll explain a little bit, how that works. Obviously, simplifying network operations. If you're eliminating layers of the network, that network should be easier to operate. It's easier for me to stand up here and say that. And we have to find ways to make networks easier to operate, and that's things that we're continuing to work on. And hand in hand with that goes into faster turnup. If I don't have to talk to the transport guy or open a transport ticket to get a new circuit between two routers, obviously that makes things much faster. What it doesn't solve, and this is my thing, you can't completely get rid of the optical transport guys. You still need to do wavelength planning. There may be less of it, but you still need to figure out which wavelengths go between each router. You still need to figure out how that works. You still have to manage multiplexing equipment, amplifiers. So you still need people with the knowledge of that photonic network that know how to manage that. And the last bullet point is really around, there's a lot of services that ride over some current networks other than just IP circuits between routers. They may be wavelength services for customers. You might have legacy TDM circuits on there, or OTN-based services that are non-IP. So we have to look in the future at how we solve those problems. I'll say in this talk, it's a bit more about the high-speed IP networks that may not have those services, but we're definitely looking to find out how we solve those other types of services through emulation, just like we did with low-speed TDM services. So this notion of wavelength utilization and how it's improved when I basically have a router at each hop. And this is sort of a pre-canned example of that, where I do have a ring of nodes, and these would be routers on this ring, where they're equally spaced 400 kilometers apart. Like I said, it's a bit of a canned example that probably would not happen so much in the real world. But between my A to Z locations, those are 1,600 kilometers apart. And really this gets into the, when you have higher speed bit rates on the optical side, there's always a trade-off with distance. So if I want to carry a wavelength, 100 gig wavelength, the longer distance, or if I want to use bit rates that are higher, like 200 gig, 400 gig, 800 gig, or even 1 terabit today, the distance I can carry that signal continues to decrease. And this kind of gets to the point that every router hop is really like it's an OEO conversion. It's a regen. So I don't really run into the penalties of carrying a signal a long distance. So I have that 400 gig signal that's really regenerated at each hop. If I'm using a direct 200 gig wavelength between those A to Z points, I can't really use a 400 gig wavelength. I have to use a 200 gig wavelength. So now at each hop, I'm limited on that piece of fiber to a 200 gig wavelength, which doesn't make the most maximum utilization out of that single piece of fiber. So really that's kind of how we unlock better wavelength utilization in this hop by hop manner. And you may say, if I've got to send that signal through every router, that's a really expensive thing to do versus sending it through the ROADM network. But those are the things that we're trying to solve in the future to make that not the case. To make sending that traffic through the routers near the cost or less costly than sending it through a ROADM network. So here's a few of kind of the innovations that are coming down the pipeline that really enable this type of architecture. 100 gig, 200 gig CAP2 DCO has been very popular in access and aggregation networks that are a bit lower speed. And you'll see almost every vendor today has a device that's some number of 10 gig ports with a few CFP2 DCO ports. Because like I said, for access and aggregation, it's become, if you want to build a 200 gig access ring, it's a very viable technology. I'll say for long-term growth and for higher speed networks, it's not really a solution. What's really the solution in the future is looking at 400 gig interfaces, and specifically 400 gig ZR, and something called 400 gig, what we call Open ZR Plus. And I've got a few slides where I'll talk about that specifically. The other things are router MPU bandwidth capacity and kind of the continuing growth in what we can carry on a single device. And IP router interface costs, other folks at Cisco may not like me to say this, but IP interface costs are going to continue to drop. And I'll talk a bit more about this complexity in optics and minimizing transceiver counts. It's a bit of a complex sentence, but I'll explain a bit what that means in a later slide. Excuse me. We look at like coherent optics. So 400 gig and 400 gig ZR, those are coherent optics. There's other talks and where you guys can learn about what coherent optics are. But what's really unlocking the density that we can supply in the future using this solution is the advancements that have allowed us to package all of that technology into a QSFP56DD form factor. And that's in a relatively short amount of time. The first couple of optics that you see there, that's really kind of an integrated on a line card optic. And then we quickly moved to CFP2 ACO, where the DSP was still on a line card. And now, it's very ubiquitous now to find a CFP2 DCO, where we put the coherent DSP on the optic itself. And very quickly, we're moving to being able to do that at 400 gig in a QSFP-DD optic. And looking at 400 gigs, this is kind of the alphabet soup of 400 gig standards. The ones that are important here are really ZR and ZR+. 400 gig ZR is an OIF, which is the optical interworking forum. It was really an initiative to have an interoperable, coherent, DWDM-based 400 gig optic from day one. And this is single channel 400 gig. Open ZR+, open 400 gig ZR+. And really the real difference between these two is the standard for ZR is really to have a 15 watt power dissipation. But people saw like other applications for these coherent DWDM optics at 400 gig in routers in the future, but they required a dissipation greater than 15 watts. So ZR+ really, it relaxes some of those requirements. It allows us to do more with the optic than ZR does. I won't go over this too much, but ZR+, it does allow you to have different modulation schemes depending on the distance and reach that you need with that optic. But the key things, this is a tunable DWDM optic. And the form factor that we're looking at, there will be varieties of this that are CFP2 DCO based, but really the key one for doing this single layer hop-by-hop architecture is the QSFP56DD, because now I can take a line card that's built for 24, 36, 400 gig interfaces and not just use gray interfaces in that. I can use each one of those interfaces as a coherent DWDM interface. This is an interesting graph that I stole from a colleague of mine that shows the growth of traffic delivered on the internet over time in gigabits versus the speed of it, the capacity of an NPU. And as you can see, the router NPU capacity has lagged behind the growth of traffic on the internet for many, many years. And people have seen that if you buy routers. Line cards have either lots of NPUs or you need lots of devices. But now we're finally getting to a point where we have very specialized NPUs, especially in cases where I'm handling a lot of aggregation and transit traffic and not a lot of queuing, not a lot of high touch services. We're building very high capacity NPUs that are soon going to eclipse 10 terabits per second in a single NPU. Like I said, those are highly specialized NPUs for mostly transit traffic, but it's one of the things that really allows us to kind of unlock this architecture because it drives down the overall cost of the device, because I don't have multiple NPUs to cool, to power, and it just overall lowers what that individual interface cost is. This graph gets to sort of what I was talking about with the minimization of transceivers. And what it's comparing is the total cost of an interface broken down by what the router host interface cost versus what that optic cost, that pluggable optic costs. With 10 gig, most of that cost was still kind of buried into the router itself. With 100 gig, as the complexity in the optic really gets more complicated. Obviously, with 100 gig, we're talking about 4 wavelengths with most optics that go in routers. That optic is more complex, so it raises the price of that versus the cost of that host interface in the router. With 400 gig, the optic is relatively even more complex, and just due to like what I showed previously with the NPU bandwidth, that's going to continue to drive down the cost of gigabit per or dollar per gigabit or whatever metric you want to use of what that router interface costs versus what that optic cost. So in a case where you are using a muxponder or a transponder, you really want to minimize the number of optics you're using. So if you're using a muxponder that has back-to-back gray interfaces, I have a lot of costs now in those optics that have to go into each side of that connection. So I really want to minimize the number of those optics that I'm purchasing. What this graph doesn't show very well is the kind of price compression of everything overall. So if you really had a fair comparison of absolute cost between these pills, you would see them go down a lot. And when you look at the comparative price or the projected comparative price of 400 gig at a bits per second level versus 10, it's a fraction of that. And like I said, that really kind of unlocks the cost element of this versus the way we used to do things, versus building these networks in the past were very cost prohibitive, and that's what led to these multi-layer architectures. But now passing that traffic through a router is not as expensive as you might think it is. And I'll try to quickly go through kind of a modeling example that we've done. And with this type of architecture, we've done modeling to date, I think, for over 20 networks, both already deployed networks. Like I said, this is sort of a CAN sample network. And the span of this network is around 100 kilometers, which is maybe a typical in the US regional or metro network. And this is what we would call more of a subscriber-heavy network. So there's really 4 traffic sources, and then every other side of the network is like a traffic sink, a lot of north-south traffic. So like I said, typical kind of service provider network these days. And then we do a traffic model. And really the traffic model is just north-south traffic. It's traffic from these caching sites and gateway sites down to subscriber sites. So there's really no traffic that goes in between the edge sites on this network. And like I said, this is typical